But let me tackle the hardest part first. Partial fraction decomposition. This is kind of the standard way when you talk about, I need to take an inverse Z transform. This, just like if you need to take an inverse Laplace transform in continuous time, this is what you think of, partial fraction decomposition. So let me talk about this first. First step is, remember there's 4 ways we can write x of z, factored or unfactored, and a polynomial in z to the negative 1 or a polynomial in z. You're going to write it as an unfactored polynomial in z to the negative 1. And just as a reminder from that handout that I gave, it looks like this. So z transforms are always polynomial ratios. Sometimes the denominator is 1. And you'll always write them in decreasing powers of z to the negative something, starting from a scalar number and ending up to your largest z to the negative something. You need to have scalar numbers on the left side of both your numerator and denominator. If for some reason you can't do that, then end up dividing through by z's, or z to the negative 1s, z to the negative 2s out here, so that both these numbers are a scalar. For instance, if this was the same exact polynomial we have here, but in the numerator was z to the negative 1, pull that z to the negative 1 out here, and then your numerator would be transformed just to a 1. When you do this, if these two numbers on the left of your ratio are both scalars, meaning not functions of z to anything, but just a plain old number, then your greatest numerator coefficient of z to the negative something will be m. Same thing for your denominator will be n. And to make it proper, this thing in the bottom will have to be strictly greater than this thing in the numerator. And if it's not, you'll have to do long division in reverse order. So I just said a whole mess of words. Anyone have any question what I've said so far? And then I'll talk about how to do the long division. In continuous time, the long division, you just simply did the long division directly. But when z transforms in discrete domain, you're going to reverse the order. It'll still be in powers of z to the negative 1, but now it's going to be in going from z to the negative big numbers down to a plain old scalar. Let me give a quick example. You've got an example here in your notes. I'm going to give you an example that's a little bit simpler, and I'll work it out in front of you. So how to make a z to the negative 1 equation proper. So say we have an equation that looks like 8 minus z to the negative 1 over 1 minus 1/2 z to the negative 1. Firstly, notationally wise, this is correct. We've got non-powers of z as the left. They're in decreasing powers of z as we move to the right. And here, both of our m and our n, actually I should have redrawn that to not include the negative. This is our m and this is our n, and they are both 1. And we want to get our n greater than m to be proper. So we'll divide through. And so to divide through, we're going to rewrite this. We'll write the denominator first, and we'll write it in the opposite order. Whoops. I forgot my z to the negative 1. There we go. And then I'll divide that into this. Okay. So let's do this. The question is, what do we multiply this thing by to get z to the negative 1? So we're going to multiply that by 2. So 2 times this will give us minus z to the negative 1, and then 2 times 1 gives us 2, and we'll subtract to get 6. So this whole thing in the numerator equals 2 plus 6 over, and now we'll write it the right way, 1 minus 1/2 z to the negative 1. And this is simple enough that using this one trick, you can now write your transform. Noah, what does 2 transform into in the time domain?
Would it be an impulse?
That's it. Just 2 times an impulse at n. And then Charles, how about this guy? The 6 comes out.
Is it 1/2 to the power of n times u of n?
You got it. All right, so for simple things, just simply, that's a horrible statement. For relatively simple problems that are proper, you don't even need to do partial fraction expansion after you do the division. But for more complicated things, you do need to do the partial fraction expansion. So let's go back to that. So this is a more complicated example of a partial fraction expansion. Here we had to divide through a couple of times before we got everything left over. And now the second step, this you can see just by inspection. This is an impulse at n-1. This is -2 times an impulse at n. And then this is something we got to work with. So we're going to factor out the denominator. And the form we're going to factor it out looks like this. So you firstly will find where the poles are of the denominator. And to find the poles, don't plug, this is not A, B, and C. Instead, rather, this is not A, B, and C. Instead, this is the denominator. Multiply it through by z squared before you plug it into your denominator. So I've given you this example. I've isolated the denominator here. I've multiplied through by z squared. And now it's just a plain old quadratic formula like you saw back in high school. You throw it in, and you get these roots. Once you get these roots, these are your lambdas from up here. And you can substitute lambda 1 with 1. You can substitute lambda 2 with -1,5, which will negative times negative makes that positive. And that gives you this. And you can multiply through and verify that, in fact, when you multiply through, you get this thing. So this is just a new kind of form. This is what a factored form looks like when you're dealing with z to the -1s as opposed to z to the +1s. Okay, everything else works just like it did in EE431. So this now has 2 real roots, one corresponding to this root, one corresponding to this root. So you can break them apart into the sum of 2 things, and you'll use the cover-up method. To use the cover-up method, you identify, here's another trick. Although you found what your z's are, what your roots are, 1 and -1/5, when you do the cover-up method, it works the exact same as in continuous time. To find out what A is, you cover up this term with your thumb, and you plug in the corresponding root down here. So you can just by inspection, you can see z to the -1 is going to be 1. So every time we see z to the -1, we just plug in 1. So A is going to be 6 plus 1, and divide that by 1 plus 1/5 over here to find your A. And similar to find B, you'll find the root, you'll cover this up, and you'll plug in your root of B. Now here's the trick. There's nothing wrong with using, you already know what the corresponding root is. You found it over here, it's -1/5. You'll save a step though. You'll be able to do this faster if instead of plugging in z is equal to -1/5, and then in your head you're going to have to take the -1 power of -1/5, and it's easy to get confused. Don't. Just work, pretend that z doesn't exist, just work in z to the -1s. So by inspection you can see, what do you have to multiply this 1/5 by to make this a 0? And the answer is -5. So cover this part up, and every time you see z to the -1, just put in -5. So that gives you 6 minus 5, and down here it gives you over 1 minus -5. Do you see what I mean? You wouldn't have been wrong to plug in z equals -1/5, but it's an extra step you got to do. Instead, just plug in instead just solve for z to the -1 and plug in that directly. So now you found your a's and b's. You get this, and now it's just a table lookup to find the answer. Any questions about that? Doing partial fraction decomposition when you've got separate, unique real poles?
Sir, I have 2 quick questions.
Sure.
The first one was when we first started this example, you set the denominator equal to 0 and then solve for z by multiplying by z squared on both sides, right?
That's right.
Okay. And the other thing was,
and that's the one part where I see most students have trouble, is that they forget to multiply by z squared.
and the other question was, in what situation would we use this? Is this to make something proper like the first part?
No.
Okay.
You've already made it proper. Now you've got this complicated sequence. You got to look it up on your tables, and it's not there. And instead, what is there are simpler things like this and this. So the question is, how do you convert this into something like that? And that's called partial fraction decomposition.
I'm also just curious about back at the beginning of the problem, like Fawaz just said, you got the -0.8 and -0.2. Where did those values come from?
From down here. So here's a new problem, a brand new problem you haven't seen before. And we want to factor this thing out because this does not exist in your list of tables and transforms, but this does. So we need to factor this out to somehow make this thing look like this. And how do we do that? We firstly identify where the poles are. And we find the poles by setting the denominator equal to 0 and solving. And that
Yes,
gives
sir.
us,
I just got caught up at the problem right above it again. I guess I thought that transformed into something else.
oh, no. This is a totally separate problem. Sorry. The only purpose of up here is to say that if your n is not strictly greater than your m, if your biggest power in the denominator is not strictly greater than your biggest power in your numerator, then this partial fraction decomposition won't work. It'll work, it'll give you the wrong answer. So you firstly have to make it proper. And then once you have a proper thing, then you do the PFD.
Sir, another question. For example, for the example right above number 2, the thing you have boxed in, we would, for the last term there, we would basically be doing number 2 on that, right?
Exactly.
Okay.
You'd say, hey, this doesn't exist in my tables. This part does, but this part doesn't, so we'll have to factor it. Yeah. And the only reason why it would have been nicer if I had one example that worked all the way through, but this example doesn't divide nicely, and then this example doesn't factor nicely, so I had to use 2 different examples. Is that clear now?
Yes, sir. Thank you.
Excellent. All right. So now we've covered the case where we've got unique real poles. Now you might remember that there's 4 cases: unique real poles, repeated real poles, unique complex conjugates, and repeated complex conjugates. In DSP, we're only going to worry about the case of real poles. We're not going to do the complex. That simplifies things a lot. The reason, if you're curious, is because the real power of DSP is, again, using computation, using the computer to work through directly in the time domain. So the only time that we need to worry about Z transforms is when we're doing theoretical studies. And usually in theoretical studies, we can actually limit ourselves often to real poles. The only time I've seen the complex poles thing come up is in some graduate school subjects. Your text does cover how to handle the complex poles, but I'm not going to test it, and you're not going to see it in the FE, and you're not going to see it even if you take your doctoral qualifying exams, unless you take it in digital signal processing, you're not going to see it. So this is fine.
Sir, real quickly, for A, how did we get the, so I understand B, you just get the -5. How'd you get the 1 plus 0.2 again? Could you, I'm like missing a step there.
Sure. So to find the A,
Right.
you use your finger to cover up the corresponding piece up here. So
Right.
now you just see this part of this part. And then you plug in, for Z the -1, you plug in your root. So for the root, for this part, the 1 minus z to the negative 1, what would make this 0? What value of z to the negative 1 makes this 0?
Just 1.
1. So just
Right.
plug in 1, and you get 6 plus 1
Okay.
divided by 1 plus 0.2.
Oh.
And then and that becomes 7 over 1.2 is 5.8.
Okay. Thank you.
Okay, so now let's handle, so this is with real distinct roots. How do we handle real repeated roots? How do we handle real repeated poles of this form? So we've got a numerator, and I've got a kind of a complicated example. We've got real repeated roots here. Here you can see that z to the negative 1 is going to be 1/3. Z is going to be 3. And that's a repeated pole. And then here you've got a one unique pole at z to the negative 1 equals 1/2. So there's two ways to do this. You'll remember from EE431 maybe that we kind of did the same thing, but there was a derivative operator, and the derivative just gets absolutely insane when we're dealing with negative z to the negative 1s. So instead, I'm going to say, don't worry about doing it by hand. If you have to, use hand multiplication out to try and match forms like you did in differential equations. I'm not going to give you one with repeated poles on a test. Instead, if you get one in practice, just throw it into MATLAB's residue Z form and let it do the factoring for you. But it will look like a 3 to the n term, and then a 3 to the n times an n plus 1 term, and then the your unique pole down here. So what I'm telling you is that if you have real repeated poles, or if you have complex conjugate poles, go back up here. Instead of doing it by hand using PFD, just throw it into MATLAB. And then once you break it out, then you can use your tables to take the inverse transform. So questions on PFD before I tell you how to use residue Z?